So, today's talk is about PyPy. So, first a little introduction on why we do this and why it's useful at all. If you look at some recent statistics on PyPy, then you will often see that people don't really switch to Python 3, or at least some stay with 2.7 for some reason. And of course the reason is you have dependencies to older libraries, you have legacy code, I can understand that, maybe even management. But there's one thing that made me a bit nervous, that was we have no incentive, so we have no reason, we have nothing that is exciting in Python 3, and well, you can debate if that is true or not, but people say, well, 40% at least, they say, why should I switch? It's an interesting question, and I ask myself, why should you switch from Python 2.7 to 3? So there are a couple of reasons. There are good reasons, I would say, or bad reasons. So, for instance, in my opinion, a bad reason to switch to a new version is if the old version is not supported anymore. Okay, you have to do it eventually, but this is always stressful for somebody who is relying on the old version. And also, if you have a major bug fix, of course you need to switch to the new version, but maybe you don't want to. Maybe you look for alternatives when you have to do that. So you want to keep people with using Python, so I can think of two reasons why you should switch to a new language. So first of all, because there's a new feature that you want to use, or improve performance. There might be a couple of others, but I think those two are really important. And what I think Python 3 did really well was new features. I like them, personal opinion. And we will need to think about performance a little bit here. So why do we even care about performance? From a management perspective, it's kind of a no-brainer. More speed means less service, so you save money. That's it. It's just that easy. If you can switch to a new version and get 50% upgrade on the speed, well, why not? And for all the developers, it's new possibilities. You say, oh, why do I need to switch to C or to Go when I can use Python for scientific stuff, when I can do games with it, whatever I want, without switching the language? That's a huge advantage in my opinion. So, you want to improve the language, you want to improve the speed, the performance of the language. And there's two ways you can basically do that. So the first way is improve the implementation, and the second is improve the runtime. So why do I separate this? For a long part, Python had only one implementation, which was CPython. And basically this was the specification. There was nothing apart. So if it works on CPython, it works for Python. But then there comes a time when you need to separate those two. You say, okay, there is an implementation, but there's also a specification for it. So somebody else can step in and write a better interpreter or even a compiler for the language. This is something that has been done for a lot of languages, and it has also been done for PHP and Python and so whatsoever. The second thing to improve is the runtime itself, but we will first think about the language, because this is what you get when you just run your normal version and you don't do anything, you just upgrade, then you get a new, better experience because of better performance. So I did a couple of benchmarks, and before I show you the results, there's a little warning. So all benchmarks are basically wrong. You cannot do correct benchmarks because it always depends on your use case. You should always measure yourself. So what you see is more of a trend, less than hard numbers. So I compared three languages, Ruby, PHP and Python, and just compared their relative performance over time. So first I have Ruby, And there's that little site called Is Ruby Fast Yet? And then you can basically compare the numbers over time, and you see from version 1.8.7 up to version 2.2, you have 36% improvement in performance, just by upgrading a language, just by upgrading your implementation. So that's nice. How about PHP? For PHP you have something even better, because from 5.2 to 5.6, people say it's improved by 50%. So this is from a core developer from PHP 7, and he has a nice paper on that, and his benchmarks are really complete. I like that very much, his approach, and he also compared for version 7. And there you can see it's a huge improvement, like 150%. That's nice. So people in the PHP community, they were reluctant to update. You had many versions where people did not switch to the new version because they had no real incentive. And sometimes they say, okay, performance is not better, well, why should I switch? But with PHP 5.6, the migration path was a lot faster. And I guess one of the reasons is that performance just improved compared to older versions. And I guess with PHP 7, there will also be another switch. So how about Python? Not so good. I didn't believe that myself. I have to say this was a benchmark I did myself. And of course you don't believe your own benchmarks. But from 2.6 to 3.4, I measured something like minus 10% with timeit on PyStone, which is kind of a standard benchmark for that. That was hard. You will later see that I'm not the only one who saw that. So over time, you would have something like that. These are the years now, and the relative performance, not the absolute performance of those three languages compared, but the relative improvement or decrease. And you see, it's going up for PHP and Ruby, but not for Python. It stays the same, or maybe it's getting even a little bit slower because of the new features. So, what does the official documentation say about that? And they say, well, okay, Python 3 runs the PyStone benchmark around 10% slower than Python 2.5. Yeah, that's the same that I found. And there's room for improvement. Well, duh. So we have new features, and we did a lot for the language. People are not switching, and we need to think about how can we get the rest of it to the newer version. Because obviously we know it's better, but how do they have more incentives? So one way to think about that is, why improve the implementation when you can improve the runtime? You can see that for a lot of languages. So Facebook, for instance, they ran into problems 10 years ago. No, not 10 years ago actually. More like 5 or 6 years ago. They kind of got started with HHVM. And there's kind of a trend. So you have those scripting languages, and you have different implementations, and one implementation is kind of a JIT compiled version. What that is exactly, I will tell you in a second. There's HHVM for PHP, there's Rubinius for Ruby, and there's PyPy for Python. And they all have kind of the same goal. They all want to improve the language by improving the runtime. And so what is PyPy? PyPy was developed here. I don't know, Mark, you can say something about that maybe later on. Some of the people who developed PyPy studied at Heinrich Heine University, so Armin Rigo, for instance. And it was kind of, it came from Psycho, which is also an experiment in that, making the runtime faster. So in 2007, it reached 1.0, which was a huge goal. And it's Python written in Python. And it's faster than Python, which is kind of mind-blowing if you think about it. It has a just-in-time compiler, and it's compatible with Python 2.7 and 3.4 as of now. But coming back to that thing, Python written in Python is not really true. It's kind of Python written in RPython. The difference is subtle. You have some things that you need to take care of, but most of it is plain Python. It's like some C programmer would write Python if he had to. You don't have, let's say, dynamic types. You have a single type in each flow graph. You have no multiple inheritance. You have no generators. You have de-under methods. You can't use all of them. I guess most of the reasons behind that is these are the dynamic features of Python. And maybe you want to avoid that if you want to go closer to the machine. You want to make it more compact and faster. So maybe you want to avoid something like lookup tables and vtables and dictionaries for objects and everything like that. And the second part of PyPy that is interesting is the tracing JIT compiler. You have a code base, your program, and it's pretty fast. It's okay. What you would do is do some profiling. You find some hot loop. This is where most of the time is spent. And you say, okay, it makes sense to optimize that part, but you don't want to do it yourself. You want the compiler to do it for you, or the runtime. So PyPy runs its program like normal, and whenever it finds a hot loop, which is run 1,000 times or 10,000 times, it will say, well, that's interesting, why not optimize that part? So you can give it a hint and say, when I start my loop, I say, you can enter the JIT now, and when I stop it, you can stop it now, JIT merge point. And what it does is, when it enters the loop now, after the 1,000th time, it will say, every bytecode that is executed now will be recorded. And I will record what I have until JIT merge point, and then I have a list, and I can optimize the list, say throw out all the types that I don't need, give some guarantees with guards. So you say, I guarantee you that in that part x is always an integer, or that that boolean is always true. So you can optimize the path, and then you create an assembler out of it. So you rip it out, and this is then optimized machine code. The rest of it is totally normal Python. You can run it with every interpreter, but that little part here, whenever you call that, is now machine code. And look for yourself. The result is cool. So with PyPy trunk, you get 7 times the performance of Python 2.7 out of the box. And these are not synthetic benchmarks. So they tried it with Django, for instance, and a lot of real benchmarks. You can see it yourself on speed.pypy.org, and they improve continuously. But all the talking doesn't make any sense if I can't show you a little demo on how this looks like when I really run a program with that. So demos always break. Apart from that, I have a little. Let's see. Can you read it? So I have a little heap sort algorithm here. It's sorting numbers, and it's sorting, right now, it's sorting 10,000 numbers. So not that much. On the right side, we have a script. Run heap sort example. And in there we have 2 timings. We have one timing for Python, for normal 2.7 Python version, and one for PyPy, which is a special version of PyPy. It's called PyPy STM. I will explain to you why STM later on. But it's just PyPy 2.5 or something. kind of cool. So same function, and now let's execute that. You will see the first output will be Python 2.7, and the second will be run by PyPy. So this is 273, 47 milliseconds per loop, 10 loops. So it does best of 3, and down there you have 7.8 milliseconds for PyPy. So, well, this is a huge improvement. You can say it's just around 7 times performance, so that's cool. So for single-threaded serial programs, this works really well. Of course, sorting algorithm is kind of the first thing some language enthusiasts will try. So don't take my word for it, just try it yourself. And now I can't reach my own. But that's not it. I mean, now you have single-threaded performance, which is okay. But maybe you want to go one level deeper. Give them an incentive to switch. We have Django support, we have a JIT compiler, we have compatibility with 2.7 and 3, we have basic ARM support now, so you can run it on whatever embedded system. But you want to have all the extensions in there, so C extensions. You want to have scientific support, so NumPy. You want to have multi-threading support, because people might want to switch to Go if they don't have another choice, or Rust, or what have you. So, improve compatibility with C extensions is really hard. There's something like C types, and you can write a C extension in there. And it's kind of compatible, but it's a mess and it's really hard to write. So what they suggest is use CFFI and port your extensions. And then you can use it. And it also works with that modified runtime that PyPy offers. So the second project is NumPyPy. This is not a typo. There is basic NumPy support, but I guess what they want to do with NumPyPy, and I'm not sure about this, but I guess they want to write it in RPython, at least part of it, and improve the performance in native Python. Because NumPy itself is kind of a big C extension. But the stuff that I'm most interested in about is multi-threading support. What is multi-threading support? And why do we need it in Python? So when you have a program like rasterizing an image or having some difficult calculation, you want to spread it up into processes or threads. And in Python you can't do it that easily because every thread runs one interpreter, but the interpreter gives the so-called GIL to the next thread. So only one thread can run at one time. Thread 1 starts, and when he hits an I/O point, then he will give the GIL to another thread, and that will run for a certain amount of time, and so on and so on. And every n ticks, it will check, can I get the GIL now? Can I work now? So whenever you do that, and you can't get the GIL, it's wasted time. What happens when you see this happening on a real machine? So this is a cool tool, GILviz. You should try it. What you see is 2 threads, and they fight for the GIL. So think about it like one thread does one part of the calculation, and the other does the other part. And every time you see a green tick, this means a thread acquires a GIL. So the first thread has it for a couple of microseconds, and then you see the red bar here, and that means give me the GIL, and you can get it because the other one has it. And now give me the GIL again, okay, which works. But then you can see a lot of red bars, and that means the first thread is basically blocked. So what can you do about that? It's pretty hard. You would think with something like this, if you are not experienced in parallel programming, you would think a parallel program would run faster. But, of course, you hit the wall. So this is an example not by me, but by David Beasley. And he compared just the runtime of a threaded program against a non-threaded program. On the left side, you see the sequential run, and it's actually faster than the non-sequential run with threads, because they are fighting for the chill. And in PyPy, they had a really smart solution, I think. What they do is they have something similar to databases. In databases, you can have multiple clients, and they can run multiple transactions at the same time. And as far as they don't access the same shared memory, it's all fine. They can do whatever they want. You start a transaction, you modify one table, fine. If the other thread or the other client does not modify it, well, you can commit it. But if the other one modifies it, then you have to roll it back. So this is the same for PyPy. They have software transactional memory. There's also hardware transactional memory in the Haswell CPUs, but they ran into some limitations for bigger programs, so they stick with that currently. You have those T points, and these are transaction points of threads. So at the first transaction point, thread 1 wants to modify X, and thread 2 wants to modify Y. And that's perfectly fine, because they don't interfere with each other. But at the second transaction point, both want to modify X. And that's tricky. So what do you do now? You cannot commit both of them, but you should commit one of them. So this is done by chance. You just say roll one back. That's it. And it does not need to be the one with the lower amount of commits. It's just one of them. So roll one back, and that's it. Then you have only the modification for X, which was only touched by one of them in shared memory, and the other one just needs to execute again, based on the new data. So this works pretty well, but how well does it work? Let's try. The example that I show you is kind of tricky. It's a bit hard to explain what's going on. What it does is a Project Euler. If you know that, that's kind of some programming puzzles that you can try. And it's one task where you have bricks of different sizes. So we have bricks of size 3 and bricks of size 2. And you want to build a wall with a certain width and a certain height. And there should not be a crack in there. And the crack means you have 2 bricks, and exactly on top of it you have the same bricks. So you have one clear line between those. You want to avoid that when you build a wall, because otherwise somebody will kick it in. And there's a kind of dynamic tool that calculates that. I did not write it myself, but it's a nice explanation, because you can split the task up into the lines of the wall. So you can basically say all the threads start with the lowest level, and every thread looks into a basis based on that. So you say, okay, maybe you want to start with a combination of a brick 2 and another 2 and a 3. And the other one might want to take a 3 and a 3. That doesn't match up, but you get the idea. So you have different combinations to build that wall, to not have a crack in there. The details are not that important. But what you will see is, let's compare the 2 versions. You have a process-based version, and then you have a thread-based version. And I will run both of them, and I will time them. So first will be the process-based version on Python 2.7, and then the thread-based version on Python 2.7, and then the same for PyPy STM. Now you know what PyPy STM means. And let's see. So what we want to build is a wall which has a width of 18 and a height of 8. And you want to get all the combinations to build that wall without having a crack. This will look pretty weird now. And maybe I should put in a sleeve actually. So first 273.
Salt again.
Sorry?
Oops.
That was of course my intention. Thanks. So these are processes on Python 2.7, all fighting for the chill, 70 milliseconds for processes. Now you have the threads, 11 milliseconds. Now you have the same for Python STM. And you can even see the chit kicking in now. It's getting faster at the end. But still 306 milliseconds. So really, really slow compared to the other one. So this last example was threads. This is now threads with PyPy STM. This is what we want to optimize. And I guess you can imagine we are still kind of far off, 192 milliseconds compared to something around 12 milliseconds for the normal version. So there's some parts to be optimized. You don't want to optimize that part with the processes because they are separate. They don't fight for the chill. But you want to optimize the part with the threading because you want to have a lock-free version. And STM does not have a chill. So they can all run as they want, and in the end, you merge the transactions. To see what's really going on here, you have some kind of STM lock, and what that is, oh sorry, interesting.
Let's STM lock.
Yeah, but I need a certain tool for that. I can't find it anymore. Oh, maybe it's here. Oh yeah. So I will open that. And what you will see is the conflicts while fighting for the chill. So X means conflicts. And you have a lot of failed transactions here. Some of them are working quite okay, but here, well, not so much. And you can see here something like acquire a lock. It only happened once that it was succeeding and the rest was failing. And this is the price you pay when you have STM compared to real threading with some locks or something. But I still think that this approach is useful in the end. Because you don't want to deal with locks, you really don't. You want to deal maybe with channels or something, but not on that low level anymore. So what we want to have is improvements for all the languages, for all your code, automatically. So right now it's good for sequential tasks, it's okay for parallel performance, they're working on it, and it's a very important Python project. Sorry for taking so long, but still have any questions?